Good morning, everyone. Now we are going to start a second part of our podcast here. We talked about ionization energy in our last podcast, and hopefully you're thinking, well, if ionization energy is the energy needed to remove an electron, there must be something opposite when we are going to add an electron, and you're exactly right. And this is called electron affinity. And electron affinity is not in our textbook. It is, and we're not exactly sure why it's been omitted. It is in your AP Chem book for those of you that are going to be taking that, and it's just a quick little thing. It's just the opposite of ionization energy. It's called electron affinity. And so it's the change in energy when an electron is added to a gaseous atom. So again, remember that the electrons that are going to be added or removed, those are called our valence electrons, and you should recall that our valence electrons are our outer shell electrons. Those are the only ones that are going to be able to move around. So our first example here is an exothermic example. You should remember that exothermic is negative, meaning that the energy is being released. So that should make sense to you that if I'm adding something, if I'm adding an electron to a system, some energy has to be released out of the system to create that stability. This is a very stable situation. This is going to happen so that things become more like noble gas configuration. So again, I just have my element X. I'm adding an electron in. In order for this to happen, that energy has to come in and has to be released. It's not coming in, sorry. The energy is being released. And when that happens, you should recognize that now I have made an anion. An anion because I have a negative charge and I have an ion that has a -1 charge, or -2 if you gain 2 electrons. So you can see for the chlorine, here's an example. My chlorine is taking in an electron. When you take a look at that, if you look at your periodic chart, here we are right here with chlorine. It makes sense that it wants to add 1 electron because then it will have the noble gas configuration of argon. So this is electron affinities. You should be thinking, yes, that makes sense. Non-metals, they want to gain electrons. And for the most part, all year long, we've been talking about them having a negative charge. So energy is released. The anion is more stable. All right, in an opposite situation, we will have an endothermic example, meaning that the energy is taking in, and so you have positive exchange here. So if I have some sort of element A or X, it doesn't matter, that electron is still coming in because we are talking about electron affinity. The energy is endothermic. This is not very stable at all. Take a look at magnesium. You guys know that that is a metal. I would hope that you would look at that and be like, that really looks weird. Magnesium with a -1 charge. If I take a look at where it is on the periodic chart, you'll see that it's on the left-hand side. This really wants to lose electrons to gain to noble gas configuration. So if magnesium is in a situation where it's forced to take in that electron, it actually is less stable than here in its natural state. So it doesn't want to happen. It's not going to happen very easily. And that's why you can see the energy here is an endothermic reaction. So the energy is being absorbed. This is less stable. It's not going to happen very often. Okay, so if we apply this trend to the periodic chart for electron affinity, you really need to make sure that you write down the word that this is generally true. These are general trends. They're not always going to be true, but for the most part it'll work. And by the way, I don't think I mentioned this with ionization energy, that you will be getting a gold sheet that has all these values for the first electron. So as I go across my electron affinity, and we'll abbreviate that, as EA, talking too much, imagine that, my electron affinity becomes more negative. So as I go across in my period, the electron affinity is going to become more negative. And what the result of that is then is that it's going to reach more stability. So it's going to do that to become a more stable ion. Then as I go down my family, my EA, my electron affinity, is less negative. In some cases, it's going to become an endothermic reaction, and this means that it also is less stable. And again, these are general trends, but for the most part, they are going to work. And again, keep in mind that, you know, our transition metals always throw a little loop there. So really, we're looking at the representative elements, which are these two columns here, and then our nonmetals over here. All right, that's it for electron affinity, nice and short, opposite of ionization energy, and hopefully you're getting a more appreciation of this incredible periodic chart that Dmitry Mendeleev designed for us. Have a wonderful day, and I can't wait to see you back in class.